Imagine an agent running overnight. The activity log is moving. Tool calls keep appearing. Tokens keep accumulating. But when you compare the system before the run with the system now, nothing meaningful has changed. The same request is sent again, the same error returns, and the agent interprets another attempt as progress. This is the dangerous part of a runaway agent. It can look active while remaining trapped in one state. In this guide, you will build a practical stop system around 3 questions. Did the state change? Is another retry justified? If the run stops, can it recover without repeating work that already succeeded? You do not need a perfect model or a complicated control plane. You need observable state, a bounded policy, and a recovery record. We will walk through a concrete example, show why common prompt-only fixes fail, and end with a checklist you can apply to an automation, a coding agent, or any tool using workflow. The payoff is not that failures disappear. It is that one failure cannot keep spending time, calls, and attention without a clear end. A tool using agent is a feedback system. The model reads the current context, chooses an action, receives an observation, and decides what to do next. Iteration is normal. A research agent may open several pages. A coding agent may run a test, inspect the failure, change the code, and test again. The problem begins when the feedback path no longer produces a meaningful change. A parser rejects the same malformed response. A browser returns the same block page. A tool call succeeds technically, but writes the same value that was already there. The next model turn sees nearly the same evidence and chooses nearly the same action. Recent agent frameworks expose turn limits because the loop needs an external boundary. Research on infinite agentic loops also treats unbounded feedback paths as a distinct engineering failure, not simply a bad prompt. That distinction matters. If you blame the prompt alone, you may keep rewriting instructions while leaving the runtime free to repeat. The safer model is layered. Instructions guide behavior, observations reveal state, and deterministic controls decide when execution must stop. The agent may recommend another attempt. The runtime still decides whether that attempt is allowed. A retry is useful when it has a reason to produce a different outcome. Maybe the service reported a temporary condition. Maybe the agent changed one input. Maybe a human supplied the missing approval. No progress repetition is different. The action is materially the same, the relevant state is materially the same, and the failure class is materially the same. Start by naming the state that matters for the task. For a form workflow, it could be the destination record and the last processed event. For a coding task, it could be the test result, the changed file hash, and the current error signature. For a content workflow, it could be the artifact hash, review decision, and unresolved issue list. Before the step, capture that state. After the step, capture it again. Then ask a narrow question. Did the action move at least one required field toward the goal? This is stronger than asking whether the tool returned success. A successful API response can preserve a wrong value. A completed shell command can leave the failing test unchanged. Progress belongs to the task state, not the transport status. Once you define progress this way, the breaker can act on evidence instead of intuition. A useful snapshot is small enough to compare and specific enough to matter. Do not dump the entire system into the agent and call that observability. Choose a compact set of fields. Include the step identifier, the intended result, the actual result, the artifact or record hash when available, the error class, and whether an external side effect occurred. Normalize values that change without meaning, such as timestamps or request identifiers. Then serialize the snapshot in a stable order and calculate a fingerprint. The fingerprint is not the judgment by itself. It is a fast signal that the state may be unchanged. Pair it with a human-readable difference. For example, expected the phone field to contain a phone number. Actual value still contains a segment label. Or, expected one failing test to become green. Actual failing test and error line are identical. The snapshot should also say what must never be repeated automatically. Sending an email, charging a card, publishing a message, or deleting a file has a different risk from rereading a document. By recording the side effect class, the recovery policy can be strict where repetition would be costly and more flexible where another read is harmless. Now add an action fingerprint. Combine the tool name with normalized arguments, the result class, and the before and after state fingerprints. If the same combination appears again without an intervening state change, label it a repeated no-progress attempt. This catches more than an exact text match. An agent may add polite words or reorder harmless fields while performing the same operation. Normalize the parts that do not change the meaning, but do not normalize away the target, permissions, amount, or other safety-critical values. Show the fingerprint in the trace so a reviewer can understand why the breaker fired. In our example, the agent calls a lookup tool with the same record identifier. The tool returns the same missing field error. The destination record hash is unchanged. The second attempt may be understandable. The next identical attempt is not new evidence. At that point, the system should require a changed plan, changed input, or human decision. This approach also improves debugging. Instead of scanning a long transcript, you can see a compact sequence: action repeated, state unchanged, retry budget consumed, breaker opened. The agent is no longer the only narrator of whether progress occurred. A retry cap prevents an unbounded run, but the cap should fit the operation. There is no single correct number for every task. A deterministic read from a stable file may deserve no blind retry. A network request with a documented temporary failure may deserve a small bounded set with increasing delay. A high-impact external write may require confirmation before any retry because the first attempt could have succeeded even if the response was lost. Define the policy beside the tool, not inside a vague global prompt. The policy should name the retryable error classes, the required change before another attempt, the maximum allowed attempts, and the escalation path. Also define a total turn or tool call ceiling as a final backstop. Framework-level turn limits are useful because they stop paths your task-specific checks missed. But a global ceiling alone is coarse. It may stop a healthy long task or let a tight expensive loop repeat too many times before the ceiling arrives. Use both layers. Local progress checks for precise control and a run-level boundary for fail-safe containment. When the cap is reached, return a structured stop reason rather than asking the model to invent one. Two different loops can consume the same number of turns and have very different consequences. One repeats a cheap local read. Another calls a paid service, launches a browser, or triggers an external action. Add budgets that match the real risk. A time budget limits how long the run can hold resources. A tool budget limits expensive or rate-limited calls. A side effect budget limits actions that mutate the world. A cost estimate can be useful when your provider exposes reliable usage data, but do not pretend it is exact when prices, caching, or hidden work make it uncertain. The stop decision should not depend on one estimated number. Treat budgets as independent tripwires. If any critical budget is exhausted, the run pauses or stops. Display the remaining budget to the agent as context, but enforce it outside the model. In the example trace, the state comparison sees no change, the repeated call fingerprint matches, and the tool budget reaches its local limit. All three signals point to the same decision. The breaker opens before the next call. The system writes a review package containing the last useful state, attempted actions, unresolved error, and recommended options. Stopping safely is only half the job. The next run must know what already happened. Create a checkpoint after each meaningful completed step. The checkpoint should include the artifact hashes or record identifiers that prove completion, the external side effects that occurred, and the first unfinished action. When recovery begins, verify the checkpoint against the current system. Do not trust a stale success flag. Confirm that the expected artifact still exists and that its hash or status matches. Then continue from the first unverified action. If the previous attempt sent a request but lost the response, use an idempotency key or a readback check before sending again. If the tool does not support safe replay, route the case to a human. The recovery record should be concise enough for a person to audit. What succeeded, what failed, what is safe to retry, and what needs approval. This prevents a common failure pattern where the breaker stops one loop, but a supervisor immediately restarts the whole task and recreates the risk. Recovery is not a new run with amnesia. It is a continuation from evidence. Several popular fixes help, but none is sufficient alone. Telling the agent, "do not loop," is useful guidance, yet the model may not recognize that two observations mean the same state. Raising the turn limit gives difficult tasks more room, but it also gives a true loop more room. Retrying every exception treats permanent, permission, validation, and temporary failures as if they were equivalent. Watching token usage after the run tells you what happened, but does not stop the next call. Even a successful tool response can hide a semantic failure when the wrong field changed. The control system must combine model judgment with deterministic evidence. Let the model explain the intended next action and propose why it should work. Let the runtime compare fingerprints, enforce permissions, check budgets, and block a denied retry. Let a human decide when the evidence is ambiguous or the side effect is sensitive. This division of responsibility is practical, not adversarial. Models are good at interpreting messy context and suggesting alternatives. Deterministic code is good at counting, hashing, matching policies, and refusing an out-of-scope action every time. The strongest system gives each layer the job it can actually perform. Here is the complete workflow. First, define success in terms of the final task state, not a green run status. Second, capture a compact state snapshot before and after each meaningful action. Third, fingerprint the action and its normalized arguments. Fourth, classify whether the result is retryable and require a reason that the next attempt can differ. Fifth, enforce a small task-specific retry cap, plus a run-level turn or tool boundary. Sixth, add separate limits for time, expensive calls, and sensitive side effects. Seventh, when a breaker opens, write a structured review package instead of a vague failure message. Eighth, recover from a verified checkpoint and confirm completed external actions before any replay. Test the system with a known no-progress case. Make the same tool return the same result twice and verify that the trace shows unchanged state, consumed budget, and a clean stop. Then test a legitimate recovery where the input changes and the next attempt succeeds. A safe agent is not one that never encounters failure. It is one whose failures remain observable, bounded, and recoverable. Count changes, not activity. When the state stops moving, the run should stop too.